The one that we had on Monday were the following. Question number 1. First of all, the question was saying to differentiate each of the following. Differentiate each of the following equations. That is the question that we had. And the first, that's a statement. The first question was number 1 in Roman numerals, y is equal to 7x raised to power -3. Then we were adding a 4. So we were told to find the dy dx. And according to what we said last time we were here, we said that when you have a 7x raised to power -3 with a constant term 4, we understand very well that this 4 is being raised to power 0, just for the sake of explanation. And then said when you are differentiating, you get the power in the form in which it is, you multiply with a coefficient. Now remember, this coefficient is having x. So when you multiply 3 and the -3 and the 7, it will give us -21 with its x value. But this -3, we are saying after doing that, we need to subtract a 1. It's a rule, and it's always we have to subtract. What else do we have? We have a 4. Now, at this point, we are doing the same thing. We are multiplying this power and the coefficient. But one thing that we need to know is that any number raised to power 0 or any term raised to power 0, it's 0. So when you multiply 0 and a 4, we are having a 0 with x, and with a 0, we subtract a 1. But for as long as the coefficient is 0, this 0 multiplied by whatever we have, the resulting answer will still be 0. That's why we just ignore it. This 0 is not even indicated. That's the reason as to why in certain situations, they will just guide you by saying the dy dx of a constant always gives out a 0. The dy dx of a constant will always give you a 0, and in short, you just ignore it. And therefore, our final answer will be -21 x, and the power here, because the power have the same sign, so we are going to keep that sign and we add their numerical values, and this is how the answer came to be. Number 2. I think these other ones were okay. I'll just do number 2 as well as number 3. So number 2, what did we have? Number 2, we had y is equal to -8 over x power 4, and then to this term we were subtracting a 3. So now, because we have done more than one of the differentiation, certain steps we will be ignoring them. Steps such as the dy dx of a constant, it gives a 0, so you ignore. That means even this part will be ignored. And therefore, if we are to make sure that this power becomes this term is written in the way that we can understand, we can write it as -8 x power -4. This thing was reciprocated. That's how it was written this x with power 4 was written as a denominator. In a similar manner here, we are going to multiply the power and the coefficient. Now we can clearly see from here that both the power and the coefficients are negative. Therefore, when we multiply them, we're going to get a positive value. So 8 times 4, definitely this gives us 64. X. To this negative 4, when we subtract a 1, we will have negative 5 as the answer. So this is where our answer was going to. Not 64, rather, it is 32. Sorry. So 4 times 8, that is 32. Then lastly, number 3, I think that's where we will end. Our number 3 was y is equal to 1 over x. This part here and this part here are nearly the same. These two are nearly the same. What did we do? We kept this numerator with its sign. We kept it. So in our case, the numerator is 1, which we will keep. And what did we do here? We made sure that we had taken this denominator way up, and the only changes we had made was the power, which changed its sign. So here, because this x does not have anything written on it, the power is 1. And when this thing goes up, we will have it x power negative 1. But in most cases, when the coefficient is 1, you don't write it. But we know that initially the 1 is there. So in a similar manner, you will multiply the power and the coefficient. So 1 times negative 1 will give us negative 1. But this one is the coefficient which will have x, like I had indicated when the coefficient is 1, mostly you don't write it. So it just remains x, but we know that the 1 is there. The power is negative 1, from which we are subtracting a 1. Like we indicated here, when the powers have the same signs, we'll keep the sign, and then we just add the values. So this would give us negative x minus 2. So this is how the answer was coming about. Juanita, are you okay now?
Yes, I am. Thank you.
You are not welcome. This is now we today have to make a step, and our step will be on our step today will be on the application of calculus. This thing we are calling calculus, every now and then calculus, every now and then. Why on earth do we even have to learn about it? Where are we going to apply it? So we'll say that the application of calculus is what we are discussing today. Application of calculus. There are many applications that we have, of course, but the only one that is applicable at your level as well as higher levels is that the calculus helps us. Now, not just the calculus, by the way, it is the differentiation. Remember I said the calculus has got 2 branches, differentiation as well as integration. But we have just talked about differentiation. Therefore, the application of calculus we are talking about is that of differentiation. So we are saying that it helps us to find the gradient of a line. It helps us to find the gradient of a line. So supposedly you are given 2 points in one way now. We go back to the coordinate geometry. When you're given 2 points and they ask you to find the gradient, if you feel, let's say you're given a line, of course, you're given a line, then they ask you to find the gradient. My dear, the best thing that you have to do is find the dy dx. That dy dx, the answer you'll find, remember what we said, that the answer you find after differentiating, it's called the derivative. That derivative is also called the gradient function. So meaning, when you do the dy dx, that function you are having is a gradient function. If they have given you the value of x at that point, when you do the dy dx, just get the value of x and plug it in there, the value you are going to find, that is the gradient. Let me show you some few examples. So let's look at examples. And mostly these examples, we use the dy dx, the application, mostly we have them in mathematics paper 2. When you're dealing with polynomials in mathematics paper 2, mostly that is where we have the greatest application of this dy dx thing. Of course, now you see mathematics, they'll just say find the gradient of a line at a point. So meaning they will not guide you which formula you must use. So let me show you something. This question here says, is it even here? There you are. They have given us a gradient. They have given us the question. They are saying, the following, there's a diagram, there's a bit of a diagram, or maybe let me just do this so that you understand it better if I show you the actual scenario, because maybe writing may be a bit of trouble for you to connect. So pamphlets, not these pamphlets. Then let me show you mathematics paper 2, this one. So we'll be running through these different past papers, one after the other, where it involves the gradient. That is where we are going to focus. This year, this is 2020 internal. Paper 2, of course. So I was talking about the polynomial, the questions that come like this one here. But unfortunately here, there was nothing like a gradient. So we'll pass. We'll go to the next one. This is 2020 now, GCE. Let's look at the question that came. Unfortunately, it was not there. There is. Question 11. So look at the question. The question is saying, some plotting that you come and do later, but I'm just focusing on the gradient because by now we haven't yet looked at how to plot. So they have given us a function. This is our function. So at some point you will be required to draw a graph where the minimum value, maximum, turning point, blah, 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 blah. All that will come later. But what I'm interested in is this question. Use your graph now, except that here I have to guide you, except that here they're saying use your graph to find the value, to find the estimate of. Now, the finding of a gradient, there is another way, the one you learned in coordinate geometry, the y2 minus y1, x2 minus x1, those things. But now I'm also trying to show you how can we use calculus in finding the gradient. So look at the question that we have. And they've told us that we are finding the gradient where x is negative 2. So therefore, when you write down this question, y is equal to 3 minus 5x plus x squared plus x power 3 plus x power 3. So what do we do here? We are going to do the dy dx, which is dy and the dx. We understand how to go about it. So meaning in my calculation, I will not focus much on the stepwise kind of calculations. Like I indicated, this is a constant value, meaning the dy dx of that thing give us a 0. We ignore it. On this thing, the power that we have is 1. So when we multiply 1 times negative 5, will give us negative 5. Now to this negative, when you subtract a 1, we are going to have the overall power, which is 0. This 0 is sitting on x. Therefore, this x becomes 1. And when that 1 is multiplied with a 5, it turns out to be just a 5. In simpler terms, when you have the function, let's say 4x, the dy dx of this function, the dy dx of this, just remove the x. Just remove the x, and the coefficient becomes the answer for the dy dx. And the explanation that I've given here just justifies that. Because the power here is 1. So 1 times 4, the coefficient will not change. And because the power is 1, when you subtract another 1 from the 1, it becomes 0. This 0 is sitting on x. So x raised to power 0, it's 1, meaning we are saying 4 times 1, and the answer just becomes 4. That is how the negative 5x has just given us negative 5 as our dy dx. Plus, our coefficient here is 1. The power is 2, so 2 times 1, it will be 2. From this power, we remove a 1. The power just remains 1. And when the power is 1, we don't write it. Plus, the power here is 3. The coefficient is 1. When you multiply the power and the coefficient, we'll have 3x. To this 3, when we subtract a 1, we are going to remain with a 2. So the dy dx here has ended. Meaning what we have obtained is our gradient function. What we have obtained is our derivative. But they are saying find the gradient at the point where x is equal to 2. We can see clearly here that we have got x here, we have got x here, meaning wherever x is, we are putting that 2 that they have given us. And then when we compute, the resulting answer we will have is that which we are calling the gradient. So if we are to now compute it, this is what we'll get. So we will say that, now remember the gradient symbol is m, so we'll say m is equal to negative 5 plus this 2 is multiplying an x, and our x is 2. The power is 1 plus This 3 is multiplying x, and our x is 2, which is being raised to power 2. And therefore, we would say that -5 plus 2 times 2 definitely is giving us a 4, plus 2 squared means 2 times 2, which is giving us a 4. So we'll say, first of all, we'll have a 3. Now this 3 is multiplying everything in the brackets, which is 4. Yes, Peso?
Two or one and not two.
Sorry?
Isn't the 2x raised to power 1 and not 2?
Look here. Here what we have is 2x, meaning the power which is here is 1. After doing the dy dx, we are not substituting in the original equation. This is our gradient function. Therefore, we are substituting the values of x in the gradient function so that we find the gradient. You still don't get it?
No,
Okay. And therefore, we will say that -5 plus 4 plus 3 times 4 gives us a 12. These two here are giving us a 16. Then from which we subtract a 5 and our gradient will be 11. That is our gradient. So the best is find the dy dx. When you find the dy dx, the answer you will find, which is a gradient function, that is where now you are that's where now you are substituting the values of x which they have given you. That is how you find the gradient. Any other questions? Juanita?
No, I'm fine. Thank you.
Risha?
Understood.
We go to the other one. I'll be more careful now. So look at again this question that we have. Says we are given the function. We are given the function. Our function is here. Our function is here. And then they tell us to find the estimate of a gradient. Remember, like I'd indicated, I've just used this example to show you that we can also find the gradient using calculus. However, the answers you find in calculus, most of them are exact. Yet the question is saying, find the estimate, meaning the formula that we have to use is that of coordinate geometry. I've just used this so that I also show you that we can find the gradient using calculus, the differentiation as one of the application of calculus. So the question that we have here is y is equal to x power 3 plus 2x, then you subtract a 1. the first thing that we must do is a dy dx, which when we do the dy dx, remember here, we'll now just be hammering the answer. The answer is 3x squared. Unless there's someone who does not understand where it's coming from. The coefficient is 1 here. We multiplied these two. That's how the coefficient became 1. To this power, we subtracted the 1. That's how the power was a 2. Plus, here the power is 1. Remember I said the dy dx of a function with the x variable raised to power 1, just remove this thing and the coefficient becomes our dy dx. Secondly, the dy dx of a constant term, the term that does not have a variable, gives us 0. As a result, that is ignored. So this is our gradient function. This is our gradient function. And they've told us to find the gradient where x is 2. This is why we'll ignore it, because our main point of focus is x. Because we do not have a y here, we only have an x. Therefore, that is where we're going to put our value of x here. So meaning now our gradient will be 3, where there is x. Where there is x, we are going to put a 2. And this 2, remember, is squared. Thereafter, we are coming to add a 2. This 2 is just right over here. We know that 2 is being raised to power 2, so we are saying it is 2 times 2, which gives us a 4. Now this 4 is being multiplied with a 3, which is outside the bracket. Thereafter, we add a 2. So 3 times 4 gives us a 12. So this 12, we add a 2. And therefore, our gradient is gonna be m is equal to 14. So the gradient of a line where x is equal to 2 is 14. That is how partially calculus is applied in mathematics, where we are told to find the gradient. However, mathematics or calculus has another application, which is just more or less like the one that we have looked at, but except that that application is talking about the turning point. When you have a graph, those I started with the online some few weeks ago, we were talking about how to find the points on the x, along the x-axis, along the y-axis. Now, there is a point here. You can see the graph. From here up to that, it was increasing. From here up, from here up to here, it was decreasing. Therefore, this point here is what is called the turning point. Though this one is called the maximum turning point. We also have graphs that go like that, sketches that go like that. So you will find that from here up to somewhere here, the graph was reducing. From here all the way up to there, the graph was increasing. So this is also called the turning point, but a minimum turning point. Now there's something that you need to know. Something you need to know is that at the turning point, the gradient is 0. At the turning point, the gradient is 0. So meaning, at the turning point, if the gradient is 0, meaning when you find the dy dx, the gradient function that you'll find must be equated to 0, because the gradient is 0, then you can even find the value of x at the point where the graph is turning. Even if you're not there when the graph was being drawn, but by the nature of the understanding that I've just tried to give, that at the turning point, the dy dx always gives us a 0. So you find the dy dx of the function, you equate to 0, and then you can even tell the value of x at which that graph was turning. Let me show you. Let me show you what I'm talking about. Let me show you what I am talking about. So this one, let me show you just a quick one. Just a quick one. Let me show you what I am talking about. So let me show you. So let me show you how I was looking at those things. I was looking at this. Perfect. So when you have a question like this, maybe allow me to give you the next one. When you have a question like this, then they ask you to find the minimum value of y. It's the same as the minimum value of y is the same as the minimum turning point. Let me just give you this question here. This question that we have, they have given us a function. We can see the function is here. There are no numbers in this thing. There are no numbers. But they are telling us that we definitely can find the value of x here where the graph was turning, even if numbers are not there. That's the beauty of mathematics. The values on x is blank, there's nothing. But using calculus, we can tell the value of x where the gradient was, where the graph was turning. How do you do it? You have this function. So the best is to find the dy dx. So we'll say dy over the dx here will be, when you do the dy dx here, we are going to have 2x minus, when you do the dy dx here, the answer will just be 4. When you do the dy dx here, it will give you 0, therefore you ignore it. And thereafter, we are saying this, which is a gradient function, must be equated to 0, because only at this point where the graph is turning, we are going to have the gradient, which is 0. And therefore, when these two are equated, we can solve for the value of x. So we are saying 2x minus 4, when equated to 0, we can find the value of x. So we'll say 2x is equal to, now here, this negative can go there, it becomes positive 4. We divide by 2, we divide by 2, and definitely the value of x is equal to 2. That means here the value of x was 2, where the graph was turning. As simple as that. So you can find any graph of this nature for as long as the graph was turning. At that point, the dy dx must give us 0. So get the gradient function, you equate to 0, and then you will find the answer. Any questions? Okay, so I want you to quickly solve this question. Quickly solve this question. Send the answers, and then I'll give you some work. Quickly solve this question. Find the value of x at the turning point here. Find the value of x at the turning point here. Quickly solve it. Quickly solve it. Send your answer to me, then I will be able to find a way. Then I'll give you some luck.